get started. All right. Hey everybody, thanks everybody for coming. My name's Dillon Sharlet. I'm here from Intel. Aaron Kunze is also here from Intel, and we work with Stephen Junkins and Deepti Joshi. Our project we've been working on lately is called Shevlin Park, which is a prototype implementation of C++ AMP on OpenCL. And it's built with Clang and LLVM, so that's why we're here to talk to you about how this is done and fill you in a little bit. So first, I'm just going to give just hopefully enough introduction to Cielos Amp to help this presentation make sense if you're not familiar with it already. And then we're going to talk about the details of the Shevlin Park itself, which is how we implemented it in Clang and LLVM. And then finally, to prove that this Frankenstein compiler works, have a little bit of a performance analysis. All right, so first, C++ AMP is actually a Microsoft specification that they've built for data parallel programming. It's been released under a it's a very liberal community promise license, which allows other implementations such as ours. In terms of, so Microsoft's implementation is part of Visual Studio 2012. It's built on DirectX 11 compute shader, and it has good GPU support. The CPU support is a little shaky, but it's pretty good. And then just, yeah, it's really seamlessly integrated into Visual Studio 2012. You can just kind of fire it up and use it right away. And then, yeah, just our experience with AMP is just that it's been highly productive to write code using it. It's easy to get up and running. So then I want to compare it a little bit to OpenCL. That's kind of the best way to introduce it. It's a very similar programming model to OpenCL. So OpenCL integrates host and device code with a driver API that you use from your host code. Then the kernel code is separate. In the OpenCL, you have a lot of control. It's independent of the host compiler. You can use it with any, it's a C API. It has broad platform support. It's supported by a lot of vendors. Whereas Cielos Amp is heterogeneous. It integrates the language into a single, you write both your host and device code in the same programming language. And it's pretty simple to program. It hides the driver API, so you don't have to deal with that. It's kind of similar to the CUDA runtime API, if you're familiar with that. But right now, it's currently only supported on Windows by DirectX 11. So here's just a look at some code. So on the left, there's an example of OpenCL host and device code. And on the right is just a simple AMP example of AMP code. And both of these just implement a simple matrix multiplication. And it's a very naive, it's taking the definition of matrix multiplication and just implementing it with a, nested for loops. But the thing to note is that Cielos Amp, you have your host and device code in the same, it's in the same language, and that's the key thing to observe here. I'm not going to go through the details on this slide, but basically, what I'm illustrating here is that there's OpenCL and Cielos Amp are incredibly similar. The differences are just in the details. We've tried to highlight a few of them here, but like I said, overall, they have incredibly similar execution models. You can map tiles to work groups. Barriers are the same. Work items, threads. It's all the same thing once you get used to it. So now I'm going to talk a little bit about Shevlin Park. So Shevlin Park, like I said, is an implementation of Cielos Amp, and it's built with Clang and LLVM that targets OpenCL to execute the kernels on either the GPU or the CPU. So we've modified Clang and LLVM and provided a library that implements the AMP specification. And then just, yeah, this implementation is not tied to Visual Studio or DirectX. So so this is just a little picture of, most of you are probably familiar with this, you can have a good idea of what we're showing here. Like we start with C++ AMP source code, which is mostly C++, but with some kernels. We run it through a modified Clang front end. And then we run it through LLVM, which includes a new pass that we've implemented that actually does all the back-end work of generating kernels and whatnot. And so I'm going to talk about the details of that here. Before I jump in, I want to give a little bit of an overview of the restrict keyword in C++ AMP, which is how, that's kind of the cornerstone of the AMP specification. So the goal of the restrict keyword is to provide a mechanism for the programmer to guarantee the compiler that their code can be targeted at devices that don't necessarily have all the capabilities that the typical host compilers do, and that they can be targeted at vector lanes of SIMD machines and so on. So some examples that I have on the right here, I mean, in particular, in restrict AMP currently, you're not allowed to use types that are less than 4 bytes. That's a relatively, I mean, that's more of a DirectX limitation than GPUs or anything like that. You can't do things like goto, which makes it really difficult to vectorize code. You can't use static variables. There's a list of restrictions, but basically they're all aimed at allowing you to execute the code in Direct3D or OpenCL or these types of APIs. And then the other key thing that it does is that it makes it so if you define a function to be restrict AMP, which says I'm not going to do any of these things that can't be done, it also means that you can only call other functions that have the same, at least the same restrictions as that function. So this is how the compiler knows that not only are you doing something in this function that we can't do on the device that you want to target, but you're also not doing any of those things in any of the functions that we call either. And this keyword, it has extended the overloading mechanism in C++. So you can do things like on the bottom left here, have an example of writing a function that's got a CPU overload and an AMP overload. And by the way, restrict CPU is basically just what exists today. If you write a function, I mean, that's basically the default restriction. If you don't write one, you basically get restrict CPU. So here's a trivial example. Just in the AMP, we return 1, and CPU we return 0. And then there's a function that implements both that calls that function. And basically what this means is that you'd be calling, if you call G from an AMP context, you're going to get the result of F. And if you call it in a CPU context, you're going to get a result, also F, but the CPU overload of it. So implementing this requires some modifications to Clang. This requires that overload expressions, or overload resolution, must be evaluated once per restriction in the calling context. And I'm new to Clang, but as far as I know, this can't be done with existing AST features. So our first approach was to clone the function declarations that are marked with more than one restrict qualifier. And then we perform the semantic analysis in each of the cloned functions. And this, I mean, we were able to get this to work, but it's difficult to clone AST nodes correctly. I mean, when we left off with this approach, it was working for pretty much every situation except when you have like a nested class with a default argument on a friend function or something like that. Like it was just, it's not a very robust approach. I was trying to use tree transform, which is not designed for arbitrary copying of AST nodes. So anyways, but that hopefully illustrates kind of the problem that needs to be solved in implementing this keyword. So the first thing that we added before that is, so we added parser support, so we can parse these keywords. And basically all the parser does is just attaches restrict attributes to function declarations. This is a little bit temporary. I mean, ideally, this would be stored on function types, which is where the restrict keyword, I mean, that's really where it belongs. So next, we modified the AST to support the restrict keyword. And basically, this means we added a new expression to the AST. That basically what it does is it allows us to fork expressions based on the restrict context. So in an AMP context, you get to say, I want this expression in the AMP context, and I want this expression in the CPU context. And this way, we can store the results from multiple versions of overload resolution in a single AST node. So we also added some restrict information to some of the other expressions in Clang, added support for the constant expression evaluators, and so on. So here's an example of what the AST looks like when we use this on the program at the upper right. So F and both overloads of F are pretty standard. There's nothing new there other than the attribute is attached to it. But then in G, you can see, so we have the new restrict overload expression, and then each branch so the first sub-expression is the amp branch, and then the second sub-expression is the CPU version. And in this case, they're pretty much identical, except for which function that the call expression is referencing. So some other things we modified in Clang, we added modified the semantic analysis to add all the diagnostics for the amp restrictions. The big change here is that overload resolution is performed for each calling context, and the results are stored in the AST node that I just showed you. And then lastly, we had to modify the code generation. So when a function is marked with more than one restrict attribute, it generates, it basically just it does the code generation once per restrict attribute on that function. We also modified some other things to support this, like the name mangling. And it also generates LLVM metadata, which is how we communicate with our backend pass. Let's see. So then we also added support for all of the code generator visitors. So all of the, when we're executing like all the visitors that select expression, we basically just cause it to select the current context being generated. And then added miscellaneous support to like the dumper printer. This makes it easier to debug. It's being, we don't want to implement just half of the stuff to make a new AST node work. So here are some examples of the diagnostics. So the first case is a function calling another one where there isn't an overload available with the right restriction qualifier. And so you can see, you should recognize, this is the standard overload resolution error, except there's basically a new candidate function, a note for the candidate being not viable because it doesn't match the restriction qualifier. And then the second example is a type that's not AMP compatible. And so this is a type that is not 4-byte aligned. So it results in a diagnostic, and it kind of shows you like where exactly the problem is. All right, so now let's talk a little about the backend modifications. So all of the modifications to LLVM, really not modifications, we just added a new pass that is responsible for a few things. It generates OpenCL functions. For functions identified as AMP restricted by the metadata, it generates OpenCL code for those. And then it also generates functions that the Runtime Library uses to access information about those kernels. So kernels in Cielos Amp are lambdas, which are functors, as you probably know. And so what we do is map functor member variables to kernel arguments in the OpenCL, and then the parameter to the lambda, which is the index argument in an AMP kernel, is basically just generated in a little bit of kernel prologue code. And then, so the OpenCL, so the kernel metadata is identified by function pointers. So we leave behind a stub for all the lambdas that are kernels in the program. We leave behind a little stub. So when the programmer tries to execute that kernel, we have basically a function pointer. And then we can basically take that function pointer and figure out which kernel in the OpenCL program that function pointer really maps to, and then get all the other information we need to provide OpenCL, such as the kernel name, the number of arguments, the pointers to the arguments and their sizes, and so on. Some other, some issues in generating OpenCL. So one issue is that LLVM has unstructured control flow, and OpenCL is structured control flow. And so this is not ideal. It would be a lot easier to generate OpenCL from the AST, but we're hoping to intercept Spear, which would be an appropriate target for this. This may be a little bit of putting the cart before the horse, but we don't need that today. But there are a lot of things that we would like to do in the future where we kind of need to go through LLVM with the kernel code. And so, for example, we want to be able to possibly in the future, there's no reason we couldn't perform the same loop optimizations that are done on standard loops to kernels. So if you have loop invariant or kernel invariant code, I suppose, in the body of the kernel, we would at least want to leave the option open to try to move that code out of the kernel and into the host code. Things like that. So it's not things that we do today. There's nothing we do today that would prevent us from generating the kernel code from the AST, but we want to keep that option open, basically. Another issue is that OpenCL, you have to use address space qualifiers to identify pointers in the various address spaces. So basically what we do is for pointers declared in arrays or array views, which are the data containers in AMP, we know those are global pointers. And then tile static declarations, which map to local variables in OpenCL. So these are workgroup local variables. We basically say those are local pointers. And then what we do is basically just go through all the instructions in the module and propagate the address spaces through. So this way we can generate OpenCL that has address space qualifiers on the pointers where the original AMP program that the user wrote didn't. This process, it's not always possible to do this statically. You can write examples where you can't determine the address space statically at compile time. And we don't handle that case yet. It's possible to do, but we don't do that yet. So the last part of Shevlin Park to talk about is, so there's a runtime library. So the first part of it is there's just a header library that the programmer includes. And this contains definitions for all the stuff in the AMP spec. So this is like array view, which are the data containers in C++ AMP. It has all the math and atomic intrinsics or built-ins. And then it also has this function, parallel for each. And this is how you actually run a kernel in C++ AMP. This is the analog to CL, NQ, ND range kernel. It also has a bit of a little library to interface with the OpenCL runtime. And then once we get there, OpenCL, this is a standard OpenCL implementation, so it compiles and executes the kernels. So I'm going to go through a little bit of an example to hopefully make this concrete. So this is a really simple kernel. It just adds 7 to each element of an array. So you can see there's this parallel for each is how you launch a computation. It runs over each element of this data AV, which is just, this is basically a wrapper around a simple host buffer. This is how AMP identifies what memory belongs on the GPU. And then at the end of it, you call synchronize, which basically tells the system that this, I want to wait for the computations to complete so I can access them again. So this piece of code comes from the AMP library that we've developed as part of Shevlin Park. So these functions are basically, they're built-in functions that the runtime library uses to access the OpenCL program that was generated by the compiler. So the first intrinsic or built-in is just simply, it just gets the program for this translation unit. And by the way, these are, even though they're not marked static, they have internal linkage because they're implemented by the pass. If we mark them static but we don't define them, we get warnings, which is no fun. So anyways, yeah, so this just basically returns a pointer to a string that contains the OpenCL program for that translation unit. And then the subsequent functions, they take more and more arguments that identify. So the first one, the void pointer, is basically just the pointer to the member function, the function operator of the lambda that basically tells you, that gives you the kernel name given one of the member function pointers. So this is how we know which kernel to create from the OpenCL program. And the other functions do similar things. They get information about the arguments where they are in memory, how big they are. And the last one basically gives us a buffer if we need to synchronize something before we run the kernel. I'm not sure what happened there. Blank slide. So this is the implementation of parallel for each, which uses those functions. So you can see here, this is this function. It takes the compute domain and the kernel object, which contains that member function pointer. The first thing we do is just grab the program and the kernel name and compile it. And then this is a cached result. I mean, if you're the first time you call this function, it'll compile it. Every other time, it'll store the result. And then we go through the arguments for that function object and just get the pointer and size and set the kernel arguments and then enqueue the kernel. And then, so basically, you just want to point out that this the way parallel for each works, the only thing it relies on is those compiler-generated functions that we defined on the previous slide. There's no other magic going on. The backend doesn't know anything about parallel for each. It doesn't like search for it and do any kind of compile time replacements on that function. So here is what the LLVM looks like before our pass runs. So there's a function in the LLVM IR that is the definition of the lambda body. You can see the add 7 in there we've highlighted. There's a little bit of metadata that identifies this particular function as an AMP restricted function. And then all of the intrinsics that we showed on the previous slide they're declared, but they're not defined yet. So after the AMP pass runs, the lambda body has turned from a definition into just a declaration, because we don't actually care about the body of that function. All we need is a stub to get a function pointer to it. The module contains just a static string that is the OpenCL program. And then all of the intrinsics are defined. So they're concrete functions now. They're defined uniquely, as you can see from this. They're going to be defined per translation unit. So this is a look at what the generated OpenCL program looks like. So it's a little bit goofy looking. You can recognize bits of LLVM mixed in with the C and whatnot. But basically, so the arguments are the two arguments, they come from the body of the lambda, or the functor member variables. And then the prologue is generated for the index. So this is where we do things like call get global ID. And then we prepare that index parameter, since that's not actually coming from a function call or anything like that. And then this is just the entry block. There's only one block in this function. It's just a bunch of, this is basically what it takes to get a pointer to that buffer and add 7 to it. But basically, this is, so I just want to point out that, this is a standard OpenCL C. There's no, we didn't modify the OpenCL implementation at all to support this. It's just, it runs on any OpenCL implementation. Here's a look at what happens at runtime. So on the left is an example of a program, a Cielos Amp program, and on the right is what comes out of, or what gets called in OpenCL when you do each of these things. So the first time you do anything with AMP, we're going to create a context, and this is where we do, create a platform, create the context. Then when you create an array or an array view, that corresponds to a CL mem object, which we're creating with CL create buffer. And then when you do a parallel for each call, what happens is the first time you do that, it's going to grab that program object with those intrinsics, create and build the program in OpenCL, and then it's going to look at that function, the member functor, the function operator, and figure out which kernel to create from that. And then it's going to do a bunch of CL set kernel args to prepare the kernel object, and then it's going to call enqueue range kernel. And that's all there is to it for a parallel for each. Subsequent parallel for eaches, they're only going to involve, they're not going to create the program and build the program repeatedly. It happens once per translation unit. And then lastly, just you can see like the operations on an array view, such as synchronize, those correspond to NQ map buffer and so on. So next, I'm going to talk about some benchmarks. So the first thing I want to say about this is we've written a couple of workloads. They're what we're calling naive ports. So what we wanted to do is, I mean, AMP is about being easy to program. And so we didn't spend a lot of time ninja tuning our workloads to the programming model. We basically tried to write a simple program that we think somebody new to OpenCL or AMP would write. We think that that's a representative sample of, I think that represents what we should be benchmarking when we're talking about these programming models. At least in our case. I mean, it's certainly useful to talk about how these perform when you spend lots of time dialing in the implementation for a particular platform. All right, so the first thing we're going to look at is the performance on the GPU. So the first thing I want to point out is, some high-level observations. So first of all, the prototype compiler, Shevlin Park, is in blue. OpenCL is in green. And the Visual Studio implementation of AMP is in red. The first thing to notice is that generally, Shevlin Park and OpenCL basically perform pretty much the same. We're a little bit slower, basically because of a small penalty for our source-to-source translation. There's basically, if we look at the generated assembly, there's a few more instructions in the generated kernels versus the handwritten OpenCL kernels. One thing to notice is that for matrix multiply, both the AMP implementations are significantly faster than OpenCL. And the reason for this is that because of the combined host device programming model, we're getting a constant fold across the host device boundary. And of course, we could define that constant in the kernel code for OpenCL. But like we said, we're trying to represent kernels that, or we're trying to test kernels that represent an equivalent amount of work for a programmer to maintain. And we think that, I mean, it's a trivial example, but maintaining a constant value in the kernel for OpenCL, whereas in AMP we get that constant for free across the host device boundary, I mean, there's a difference there, and so we're trying to represent that. And so because that constant gets propagated across the host device boundary, loops get unrolled, all kinds of stuff happens, and it performs a lot better. The other thing to notice is that so Microsoft's implementation is built on DirectX, which doesn't have shared physical memory support. So in OpenCL, we have CL-mem use host pointer, which basically means when you create a buffer, you get to use the same buffer for the host pointer and on the device, if your machine supports it. I mean, it doesn't necessarily support it, but the Ivy Bridge is what we're testing this on, has shared physical memory support. So the workloads that have, where they don't have, the ratio of computation to memory transfer is not as high, the Microsoft implementation is held back by the performance of the memory transfers, basically. There's a lot of, these, the two benchmarks on the right represent a lot of memory transfer cost. On the CPU, so this is our performance data on the CPU. Same colors again. So the first thing to notice is that the penalty for the extra instructions that we generate in our generated kernels is quite a bit larger in some cases. There's still a bit of a benefit for OpenCL or for Shevlin Park in the matrix multiplication. That constant propagation gives us a little bit of an edge despite the extra penalty for the extra instructions generated. And then the other thing is that the warp device in DirectX is not quite as optimized as OpenCL. So basically, a little bit of analysis here. So like I said, the Cielos Amp enables these whole platform optimizations. SGEM benefits significantly benefits from this. And we also think that other optimizations are possible with more compiler education and parallel for each. I mean, parallel for each is fundamentally a loop nest. I mean, there's no reason that the loop invariant bits of code couldn't be pulled out of those loops. if the compiler understood what was happening in these programs. There is a small penalty for OpenCL source-to-source translation, but it is significant in some cases. Spear would help us a lot here, we think, because we wouldn't have to generate OpenCL C in our compiler backend. We could generate Spear, which is much closer to LLVM. It wouldn't involve a lot of the extra transformations that we're doing. So some conclusions. We think that this shows that Cielos Amp can be successfully implemented in Clang and LLVM with OpenCL as a runtime, which means that AMP can be cross-platform. Another thing, I mean, like I said, we're really looking forward to Spear for OpenCL. We think that Spear it'll help expand the useful domain of OpenCL to machine tools, so new compilers for new languages, and even heterogeneous ones like C++ AMP. I mean, we could use that to build languages that have support for both the host and the device in the same source file. And so yeah, specifically for us, I mean, we really think that Spear will help. It'll just improve the quality. We'll have more reliable code generation. We won't have to worry about busted kernels, which we get every now and then. You know, this is still a prototype compiler. It would just help a lot. I mean, it's much closer to LLVM IR. It's designed for machines and not for people like C. And lastly, just that I mean, Clang and LLVM, these are amazing tools for enabling prototype compiler projects like this. I mean, we would not be able to think about building a compiler like this with the resources that we had if it weren't for these tools that you guys have provided to the community. So thank you. And yeah, that does it. So any questions? Oh yeah, actually, if you have questions, could you use the microphone?
I had kind of two related questions. You said you take the restrict qualifier and attach it as an attribute to the function, and you don't change the function type by itself. So won't that violate like the single one definition rule? I mean, won't you have like two functions the same name and same type in the same scope?
Well, I think the part to recognize is, so right now what we do with attributes is attach two attributes to the same function. And we would want to do the same thing with function types. So the function type would support attaching multiple restrict qualifiers to the same function. And then, so that way if you're defining multiple with the same one, then they're not, you don't have two functions. And if they're actual different overloads, we've modified the overload resolution to see that. So in the semantic analysis, two functions are not considered overloads if they have, or they are considered overloads if they have different restrict qualifiers.
OK. So the second one is, if you don't change the function type, I don't know about AMP, but can you have like function pointers, which, so what is the type of function pointer that takes on the right-hand side of function with a different restrict qualifier?
So yeah, so function types and function pointers is not something that we've implemented solidly yet, but that is part of the AMP specification. It's something that we're working on. That's one of our next projects to do. And basically, yeah, there's syntax for defining the restrict type in a function pointer declaration. So when you assign that function pointer to a function, it goes through the same overload resolution based on the function types that any other function pointer assignment does.
Okay, thanks.
You're welcome.
Okay. So question, I believe this is done on a Windows platform, right? So does your workload include any kind of Microsoft header files? Does Clang have a problem with parsing those header files?
So our implementation doesn't rely on any Microsoft headers or compilers or anything at all. They're totally independent.
But what about on the host side, right? The host program may want to include some other kind of unrelated to AMP header files.
I mean, our implementation does not. I mean, we do.
So you provide all of your header files? Is that
right. I mean, we provided the AMP header file, and then everything else comes from your host platform. So, I mean, we do some of our development on Windows, and we're using Clang with MinGW. It works pretty well. But none of it is based on Microsoft headers. I mean, it would be possible. I mean, if we were able to use Windows headers with Clang, I mean, you could, but That's not.
Well, that's my question, right?
Oh yeah, but we haven't solved that. It sounds
Okay.
like
Okay.
we might be. Yeah, we tried, and it's not quite there yet. But I mean, you can still use Clang on Windows with MingW, no problem.
Right, I got that part. Okay, so another question is, now how would you support debugging under this mode, if a user want to debug their AMP source code?
That's a good question. I don't really have an answer yet. We're not quite there yet. I don't even really know much about the debugging facilities in LLVM yet. I really can't answer that intelligently yet.
Thanks.
So I can't resist asking a question about restrict and overload resolution.
Yeah, go for it.
So with this notion of the resolve overload expert, that approach is going to place a lot of restrictions, on what you can actually overload. So if you overload a function versus CPU versus an AMP version, they must have exactly the same return type, presumably.
Right, and that is part of the AMP specification, that they must have the same. Basically, any expression in an AMP overloaded context has to always resolve to the same type. That's part of the AMP specification, presumably for exactly this reason.
Presumably, they also ban const expr.
That's an interesting question. I don't know that they explicitly do that. It would certainly make things a lot easier because the constant expression evaluators, implementing this in the constant expression evaluators is really tough. But to be honest, we haven't rigorously tried to poke holes in the const.expr stuff. I mean, I've never written a const.expr function with restrict overloads. I couldn't tell you. There certainly are issues there. You're certainly right to, that's a suspect, a suspect issue.
Thanks.
For sure. Any other questions? Well, I guess that's it. Thanks again.